All right, let's see what we can do here. I've set up some things right now. I've changed the degree to 60-degree launch angle just so we could have some unique lengths. If it was 45, my velocity x and the y would be the identical approach, okay, or the identical value. So what I did is I looked at a trig triangle. That's how we work with vectors. It has an influence upward and an influence horizontally. This ends up being the adjacent side to the hypotenuse in 30 degrees, so it's cosine 30 equals Vy over 6.3. So Vy is going to be 6.3 times cosine 30. Okay, and I did that in my calculator wherever I put that, and that is 5.45. Okay, I'm going to do the calculation for the horizontal also. And that is going to be v of x, right? If I set this up, hypotenuse, v of x is over here. This is a 60 degree. Cosine of 60, so v of x equals 6.3 cosine 60, right? And that would be 3.15 meters per second. So essentially, the impact of changing the angle, instead of being 6.3 meters per second straight up, now that it's at an angle, it's got an influence of 5.45 meters per second upward and 3.15 seconds horizontally. Okay, so when we've got two-dimensional motion, the velocity upward influences how much time it's in the air, and the velocity horizontal with that time tells us how far it goes. So let's figure out how much time we've got, okay? So if I've got a 5.45, right, and let's say I'm going from, I guess what we need to do is determine where am I going from. If I'm starting from here, right, and I'm ending over here, that means I've got 5.45 this way. It also means I've got 5.45 that way, okay? So I can figure out, using this principle of if I start at the same height, end at the same height, I've got the same initial velocity and same final velocity, just different directions. I can do that in the y direction also. There's a couple other scenarios that you could do it, but I could set it up at an angle here, and I'd have an initial height, and I'd have to do some modified calculations for that. So maybe I'll do two different calculations. I'll focus on this one to this one right now. So I'm going to use, what do I want to find? I want to find how much time I'm in the air. These are my two items with time. Okay? If I start at 0 and I end at 0, I can use this equation. And if I start with the same velocity, end at the same velocity, right, I can use that equation. This has got a time squared. I don't really love that, so I'm just going to go with the easier one. So I've got a 5.45 initial velocity, and this is my final 5.45. That's where that negative went. I've got a negative 10 meters per second squared, and I want to know how much time I'm in the air. Okay, so 5.45, if I subtract 5.45, or basically multiply that by 2, I get 10.9. 10.9 was negative 10t. The time that I'm in the air, right, this shouldn't be hard for me, but I'm making it hard, right, is I'm just making it time in the air is 1.09 seconds, okay? So my vertical velocity, my vertical influence determines how much time it's in the air. It doesn't matter how fast I'm shooting it off this way, as long as wind does not play a factor. Time, right, up and down is related to these constant acceleration equations. So now I'm going to go find out how far it goes, because I know it moves horizontally in a constant velocity scenario. So my constant velocity, right, that doesn't change. It's going to be my change in x over my change in time. So my constant velocity is 3.15 seconds, and my delta x is what I want to find. And then I want to know my time, which was 1.09 seconds. So, if I set up my launcher and I put it at 60 degrees, I should be able to put a bucket, launcher height to end height, at the same level, 3.15 times 1.09. I should be able to put that at 3.43 meters away. Okay, so my final video is going to see, does it work? All right, so here are my calculations, and here is my final prediction of how far away my bucket needs to be for me to launch at 60 degrees. All right, we'll see what happens.